Yeah. Until 7
Oh my, soccer practice is a lot, huh? Didn't get home till 7 last night.
And guess what?
What?
We stopped early.
Really? And it was still 7. You know, when
Because it went dark.
yes,
Daylight
well, that's about to change though, isn't it? Well, you know, Drew's practice goes till 8:30. Monday through Friday, so I get it. He doesn't, when he, no matter if I'm driving or if he's driving or whatever, he usually doesn't get home till close to 10. Every night. It's a lot. Cause we leave here at like 3:30 and he doesn't get home till 10. Well, that's gymnastics for you. It'll wear you out. Well, soccer sounds fun. So what position are you gonna play? Yeah,
I don't remember the position.
do you remember what you're supposed to do?
Yeah, score the ball in the goal.
Okay.
And then defense protects the goal.
I was wondering if you'd be goalie and like your brother, doesn't he goalie?
No,
For
yeah,
hockey?
he
Yeah.
was goalie for soccer.
Oh, was he? He's gonna be goalie for hockey too, right?
He still is.
Yes, that's what I thought.
I don't think I'm a goalie person. I'll probably be like the person, if the goalie's not there, I'll volunteer.
You gotta have such fast reaction to be a good goalie. I'm not that quick. I'm not that coordinated in
You
general.
also gotta be
No.
ready for breakaway.
Yeah, you just have to be prepared. You know, my nephew does hockey too. Yeah, he was on an elite travel team this year. It's his first year on the team. And he, I showed your brother. I knew your brother and Andrew, because I knew they'd appreciate it, because they both played hockey, but he got his first major hockey injury, and it wasn't even that major, but it was enough. They were doing some kind of a drill and the puck hit him in the helmet, but it cracked the plastic and it forced the inside part of the helmet into his ear, and he had to get stitches in his ear. Yeah, he was really proud of it. I know, but ears hurt, like, you know, if you've ever like bagged your ear, oh, that's the worst. That hurts so bad. Your ears are so sensitive to stuff like that, so yeah, he got blood on his jersey and he was thinking it was pretty cool, so.
I get my jersey Saturday.
What color is it, you know?
Team colors are black and blue.
That makes sense.
And my coach tells me I need black shorts and black socks. So
Okay.
I think it's good.
Okay, alright. That'll be great, you got shin guards and all that?
Yeah.
Fun. It's fun.
For my dad's, it took like an hour to get there, so I had an hour to figure out the shin guards.
My Drew's godparents, all 3 of their boys are real big into soccer. Like the oldest became a referee and stuff when he got into high school, but for a paid job, like they're all really big soccer players. None of my boys never did soccer, they just did loads of gymnastics for years and years of gymnastics. And no soccer happened. But that's cool though. Sounds like
My
you.
brother played flag football, baseball for most, soccer, and now hockey. Hockey, he found out hockey is his
That's his
passion.
jam,
It's his
yeah, oh,
passion.
no, he loves it, yep, I know. Well, you gotta be committed, cause hockey's a lot of work, I know it's a lot of work, and it's like year round.
And everything costs a lot of money.
Oh, yes.
Especially goalie pads.
Oh, I'm sure they do, I'm sure they're really expensive. Do you know, do you guys have to wash his jerseys and stuff, or does the club take care of it? I found that out after my nephew bled all over his jersey, that they don't have to even, the club will do it, hey. It's like that. Yeah, I was gonna say, that's impressive because we know a lot of them stuff, so. Well, Drew has his big state gymnastics meet this weekend, so we're excited. I'm a little nervous. I want him to do really well, so. Yeah. I go out to Cartersville for state, at least we're not leaving.
Cartersville, how
Yeah.
far is it from?
Probably an hour and a half, not too bad, get there early, be there on time. We've done state in Savannah many times, and that's like 4 hours. I love Savannah, but it's a lot of driving just to go
I love the Savannah.
for a gymnastics meet.
I've never seen a game.
And then when he was younger, like up to level 5, the way it works is like,
What was
if
the lap
you're-
25?
what about it?
The lap 25?
What about?
I mean, the 24 one, the turn in.
Oh, I have it to get back today.
Oh, yeah.
Um, But it used to be like when he was on the compulsory level, so like up to level 5, 6, or whatever it is these days, 5, I think. If your team scored high enough, then your team came back for another competition on the last day. And the way they did that is it's like, listen, you know what? So like instead of everybody competing every meet, you put your best 3 on every
This is
event.
for you, Miss Dan. Read off. Warning.
Ah.
It contains a plastic baby.
I know, oh, your mom is so sweet. That was so funny, cause I was like, I need to get one of these. Oh, she's so sweet. I have to write her, laissez le bon temps rouler. I love it. King cake. Because it's Mardi Gras, well, it's, so. They call it Mardi Gras if you're in like New Orleans or whatever, kind of secularly. In church, we call it Shrove Tuesday.
That.
Well, the girls, the twins brought those for everybody because it's their birthday, so. Actually, let me grab you guys some napkins and you can actually snack on those now if you want, but let me get you some napkins. Go. So anyway, I will be, I'm unable to go to, what, I'm short a napkin? Okay, I'm short a napkin. I won't be able to go to our church pancake dinner. I have to be
Pancake dinner.
Yeah. Ooh. So for Shrove Tuesday, the tradition is that you go get, there you go, everybody's got them. All right, you're good. Is that you go get pancakes for, or you make pancakes for, oh, sweetheart, that is so sweet of you. Thank you so much. I'm gonna put it with my king cake. But that you go get pancakes on Tuesday because the idea is that it's the beginning of Lent. So you're supposed to have all of the rich, sweet and fatty and delicious things out of your house so that you can abstain during Lent, fast during Lent. So the idea is that you take all those sweet and delicious things and make pancakes with them on Tuesday. So that's why people eat pancakes on Mardi Gras. If you go to IHOP tomorrow, tonight, it's gonna be like a big old thing. So we always have like a pancake dinner at church and we usually do pancake races where like you take the, you can go, like anybody can go tonight. It's fun, but like you put the pancake in a pan, like a little skillet, right? And you have to flip it and catch it and run a course while you're flipping it and catching it. It's great fun. And we do that and we do bingo and they serve like a big breakfast for dinner, but I can't go because I have to be in Marietta. Yeah.
Well, why do you have to be to Marietta?
Because I'm the one that drives Tuesday carpool to gymnastics. So I have to take all the boys out. Yeah, I have to take all the boys out to Marietta on Tuesday. That's why I'm like, we have to leave on time on Tuesdays. Like I can't have stragglers because I try to get the email out to you guys before I leave. We leave here at 3:30. You guys don't leave here till 1:30. So it gives me like 2 hours to get grading done, tables put back, chairs put back, all that stuff, lab cleaned up and email sent and out the door. So sometimes grading has to wait till I get to Marietta. But tonight I'm gonna take myself to the IHOP for dinner all by my lonesome since I can't go tonight to church to. Yeah, I love to go, but I'm Tuesday carpool and we can't skip.
You're always Tuesday.
I'm always Tuesday carpool and we can't skip this week and find a sub or anything because our state, I was just telling Lucy, our state meet is Saturday, so we have to practice today. Like we can't miss it. It's important.
My basketball tryouts were yesterday.
How'd you do?
So I was first after just one person. And so first we did dribbling around these little orange things.
Mhm.
But on the way back, we didn't have to go around each of them.
Those your grandpa's change, by the way. I made pennies. Uh-huh.
By the way, which gym or
That's great.
which place was that?
Yeah, where are you playing?
Knobs Creek?
Is that where you?
No, I went there and I went to Oregon.
So
live?
You're wrong.
I think it might be closest-ish to Papa,
Oh,
the one closest to Papa.
we don't know where Papa is, so it doesn't matter. That's good.
Papa Performing Arts.
Oh, okay. Papa, okay. Yeah, that's where my boys first did gymnastics was at Dobbs Creek.
Fowler or.
Yeah, could be any of those. Yeah, yeah. I think she's talking about Dobbs Creek. It's up that direction. Yeah. Excellent. Well,
it's
Lucy
not-
said that she just started soccer this week. So you're doing basketball, she's doing soccer. What are you
Yeah.
girls doing these days? Lots of music? Where are you doing gymnastics? Okay, yes, excellent. Are you doing just like the rec classes? You're not on the team, you're doing the classes to first to see if you like it. Are you doing it too? Yeah? Ah,
I did that for,
very good.
I did that for a little over a year and then I stopped.
Yeah, gymnastics is good. It's very, very hard. Very, very hard. All right, so welcome to fourth quarter. Guys, do you realize that we only have a couple of classes left? Like, we are almost done. Do you realize that?
Oh, it was very quick.
Yeah, it was very fast. We have way less than 10. We have like 8 classes left. That's about it. And only like 6 or 7 of them are classes. Like yeah, we're almost on summer break. We are getting really close. It's so cool. Yeah.
I might not, I actually might be moving until I won't be able to do the biology if I move.
Oh, really? No. Where would you move to?
Huh?
Where are you moving to?
I didn't know either.
Yeah. Well, we'll see. All right, so let's go ahead and go. Let's get started. So we're talking today about reaction rates, and our lab today is going to be showing you different reaction rates. So let's talk about what is required for a, why is this like this? Okay, what is required for a chemical reaction? And let's talk about collision theory. Okay, so we have a whole theory about this. What's the difference between a theory and a law, people?
A theory is a law is what happens,
Right.
and a theory is why it happens.
Yeah, so this is explaining why we see what we see in chemical reactions with regards to how the particles may be colliding. So it's a theory. So collision theory has 3 parts. Does anybody know the 3 parts of collision theory, or can anybody give me one? Or Annabelle, what do you have? Okay, what do you have? No, okay, well, let's see. We have, for our theory, it says our particles must collide. Okay, so in order for a chemical reaction to take place, the particles have to collide. That kind of is the obvious statement of collision theory, right? They have to collide with sufficient energy.
Yeah.
That means enough energy. And they have to have the correct orientation, which means they need to be facing each other the right way. Okay? All right, so let's talk about that some more. Here's a little video that shows you what they mean by these 3 things. Sufficient energy must collide and correct orientation.
Question, like,
Yeah.
light fire into a wood. It's a chemical reaction, right?
Yes,
You
combustion.
don't light the chemical, or you don't need to face the wood the right way. So how is that a correct?
Okay, so you don't have to face the wood the right way. No, but what's happening is the oxygen that's reacting with the carbon-based compounds in the wood, those particles have to hit each other the right way. Does that make sense? And combustion is less one of those reactions that you can, well, I mean, you can time it, you can change the rate, but all right, so let's see. I've got to turn that up a bit. What do we mean by these 3 things?
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reactions, Max Trotz and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor, orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this collision of the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orientation was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react. They must have sufficient energy to break and make new bonds, and they must collide with the correct orientation. Thanks for watching this episode of
So with
Teacher's
the
Pet.
particles
Don't forget
must
to like and
collide?
subscribe and follow me on Twitter at
When
Teacher's
Eunice mentioned fire, if you don't have, if you're blocking access of oxygen, will your fire burn? No, you have to have oxygen, right? Because
Yeah.
that's part of it. So that's like if you stack your wood in your bonfire pit and you stack it in such a way that the oxygen cannot flow around the wood, you're not going to get fire, or you're not going to get very good fire. You'll get a little piddly bit of fire that won't do much, right? So you have to stack them in such a way that they will actually be able to collide. All right, so particles must collide. What makes particles more likely to collide? If they're present in what kind of concentration? Is that your hand, Emerson, or no? No. Annabelle? Present in what kind of concentration? Do you think higher or lower? Yeah, and higher or increased concentration. Okay, Eunice, if they have higher, what kind of energy? Activation is going to come from it, but what kind of energy is temperature? There's a clue there. It says temperature.
Oh, kinetic.
Kinetic energy. All right. If they have, what do you think about surface area? How's that going to impact whether particles collide? What do you think, Eunice? Cold?
Yeah.
Not cold. What do you think, Annabelle?
Freeze.
Decreased? What do you think, Emerson? Not sure. So if they have greater or increased surface area, the more surface area, the more likely things are to touch each other, right? Think about it this way. If you're in an elevator with a real skinny person versus in an elevator with a really big person, which one are you more likely to collide with? The real big person, right? Okay, because they're taking up more space, right? And there's more of them for you to bump into. You ever had that happen? I have.
Yeah.
So if they are under pressure, but this only applies to what? What do you think? What do you think pressure? What do you think?
Cold.
This applies, yeah, you're on the right track. Gases. Okay, because why does pressure affect gas in ways that it doesn't affect solids and liquids?
Because if you combine it, if you like add more pressure to gas, it will
What happens?
fizz or
Kind of. Okay, so think about it this way. We define solids as having a fixed shape and a fixed volume, right? We define liquids as having no fixed shape but a fixed volume, and we define gases as having no fixed shape, no fixed volume. Okay, so if you have no fixed volume and you are put under pressure, all those particles are now going to be closer and closer and closer and closer and closer together. So they're more likely to collide because you're condensing those same amount of particles into a smaller space, right? That's like if I took all you guys out of this room and packed everybody into the bathroom for class. No, all same amount of people in a much smaller space, right? Okay, so particle collisions affect the rate of reaction. All right, what's a rate? Do we know?
a rate is the speed in which
It can be speed. Speed over what? Do you remember?
speed over
It's time over distance. It gives you speed. Yeah, rate is like speed. So rate could be if time over distance. And the easiest one to remember there is miles per hour. That's how we travel on the road, right? What's the speed limit in your neighborhood, probably? In your neighborhood?
Oh, 20.
25 miles
I
per
think-
hour. 30.
30.
Oh, yeah.
50.
Oh, yeah,
I think it's 20 or something.
Usually, most neighborhoods are 25. And Georgia 400 is 55 to 65, though people go 80. Yep, every day. But a rate is a change, over time. And whatever that change is, it's a change over time. So particles must have sufficient energy. Particles are more likely to have sufficient energy if they have a higher kinetic energy, which we call what? Kinetic energy is temperature, right? If they have, a higher kinetic energy called temperature. So if you watch again right here, watch these particles come. Kind of past each other because they didn't have sufficient energy. But these next particles, they come really fast and they have enough energy that they combine. Because kinetic energy is energy of motion. So remember, when we're talking about temperature, we want to think about heat. That's where our brain goes. How hot or cold is something? But really, temperature has to do with motion. How much motion is there and how fast is the motion? It's about speed of motion. So you have to have sufficient energy for the particles to collide and not just bump past each other. All right. All right. Now, sufficient energy is required to start a reaction. And what do we call that energy, Annabelle?
Kinetic.
It's a type. It's a type. Yeah. Activation is what we're looking for. It's activation energy. And that is the amount of energy needed to start any reaction. You're going to have some amount of energy. And it causes particles to combine. When two substances combine, what do we call that? What kind of a change is it? You know, when two substances combine, what kind of a change is it? It's a chemical change, right? If some particles of hydrogen combine with a particle of oxygen, do you have hydrogen and oxygen anymore? If you have two hydrogen and one oxygen and they bump together, ta-da, and they combine, do you still have hydrogen and oxygen? No, you have water because it has now been a chemical change. An energy level affects a reaction's, rate. Right. All right. So particles must collide with the correct orientation. All right. So there's going to be another little graphic for you to watch up here. You good, Lucy? So particles are more likely to combine with another correctly oriented particle if they're present in higher concentration. And if they contact other particles more often, increased energy or temperature. So do you see these two? They're not going to fit together, are they? They will not make a happy couple.
Yellow looks like Pac-Man.
It does. It is like a Pac-Man. But what if these next ones come and they're oriented a little differently? Let's see what happens here. Oh, here they come again. Are these going to fit together? Yes, because they were facing the right way. All right, so if they're in higher concentration, why does that matter? If there's more of them, then it's kind of like, okay, you're looking for your dream partner, the person you want to spend the rest of your life with, your mookie smoochy. You want this lovey-dovey person. All right, and you're on an island with 10 people versus you're on an island with 100 people. Where are you more likely to find somebody you really, really like? Yeah, because you got more people, right? And that's the idea here. They're more likely to connect if there are more of them in a space. And then if they contact each other they have increased energy. So if you increase the temperature, they have increased energy. So if they come at each other facing the right way, they're more likely to click together if they're coming at each other with more energy than if they just sort of bump away, right? All right, so what affects the rate of a reaction? All right, lots of things affect the rate of a reaction. But this whole concept of what affects reaction rates is called chemical kinetics. Chemical kinetics, and it can get really complicated. Does that look complicated? Yeah, it can get really complicated. Can anybody define chemical kinetics? Does anybody know what that is?
Oh, wait. Energy affects.
Yeah, kind of. So it's basically just the study of reaction rates. There's an entire field
where all people do is study reaction rates. Where might that be useful in life? Where might it be useful to have somebody who studies the rates of reactions? Can you think of anything?
Like construction sites.
That could maybe be industrial applications. Yep. How about medicine? How about pharmaceuticals? Medications. Is it important to know how quickly or slowly a medication is going to work? Right? Have you seen commercials for medications? Sometimes they'll say like it's a delayed release. It works for 24 hours. Like they found all kinds of ways to slow how quickly your body will metabolize something, because maybe you need that medication to stay working in your body longer. Other things get in your body and your body like uses it up real quick, like it metabolizes it and moves on. And some things, some things aren't like that. Some things take days and days to get through your body. So, or months sometimes, depending on what it is. So what's a rate again? We said it a minute ago. It's what is it? Oh, Everly. Can be like a speed. Yep. It's a change over time. Okay. Change over time. So here's an example. It's showing you the number of molecules. So we have the purple ones here, and we want them to all become the green ones. So the green ones are a different compound that has been created over an amount of time. It's developing, and it occurs over amount of time. Chemical reactions are not instantaneous. Even if it's a fraction of a fraction of a fraction of a second, there's still time, right? And there are ways to speed them up and slow them down. So in this case, it's showing you the number of molecules of each color and the time. So you start with 50 molecules of purple, right? And by the time you've been through 20 minutes, about how many molecules of purple do you still have?
Like around 23.
Yeah, let's practice reading graphs. Okay, so eyes up here, people. So you see on which axis is this?
The time.
What do we call that axis? We have a letter name. We call this an x-axis, and we call this
A
one a y-axis. So on our y-axis, it's showing us the number of molecules. And what's our max number? 50. Do you see it up there? 50. And we start with 0, and then the lines are 10. Do we agree?
Yeah.
10, 20, 30, 40, 50. And then this way it's minutes. 60 minutes. So 20 minutes into our reaction, about how many purple molecules do we have?
20 minutes into our 10.
There's 20, yeah, about 10, 11, maybe 12. It's just above that line, see it?
Yeah.
And how about at 40 minutes, how many molecules of green do we have?
5.
How about, no, for green, how many green do we have at 40 minutes?
Like around 47.
Yeah, about 47. Okay, so let me see. And what do you suppose is happening where it says 30? What's
It's
happening?
starting the activation energy.
Yeah, that's what's showing you that right here at 30 is when you've got, it's almost like how do I describe it? Which is going faster? Is the purple leaving faster or the green coming in, or is it about the same rate?
About the same.
Yeah, it's about the same. So this is kind of like just past this is your midway point, right? And this is like halfway to your completion is what it's showing you. So let me see, Emerson, tell me how many purple molecules you have at 10 minutes, about how many purple? What do you think? 10 minutes and go up, and about how many particles do you have for the purple line? You see it?
25.
Yeah, about 24, 25. Lucy, about how many purple particles do you have at 50 minutes? You see? 50 minutes, about how many purple particles?
1.
Yeah, about 1. And if you look at the graphic, you can actually see just 1. All right, good. So we practiced a little graph reading there. So reaction rate is defined as the speed at which a chemical reaction takes place. And reaction rates are affected or can be increased by catalyst concentration, surface area, temperature, and pressure. We talked about pressure for gas. We talked about why temperature works. We talked a little about why surface area works and concentrations. And we still have yet to talk about catalysts. We'll come back to that. So a reaction rate is the change in the amount of reactant or product per unit of time. So if we said it's change over time, so it's a change in the amount of reactant or product divided by the amount of time taken. So a rate of reaction is amount of reactant used divided by time, or the amount of product formed divided by time. You can do it either way. All right, now, reaction rate is inversely proportional to time taken. Now, you see that? That little sign? Yeah, kind of. So this is one way you may see it written one day. So it says change in the amount of reactant to product over time taken, the rate of reaction, and then you put your number over your time taken. So you may just see it written that way. You guys aren't going to have to do it, but it may be a thing. All right. Here are different factors that we talked about. So our collision theory says they must collide. They must collide with enough energy, and they must collide with the right orientation, right? Okay. And then we have increased concentration of reactants, increased temperature, increased surface area, increased pressure for gases, and then catalysts. So here are reasons. Why do these work? So for increased concentration of reactants, it is going to, see the little arrow? It is going to increase, that's what the arrow means, because it's going up, sorry, the frequency of collisions. And that is going to result in a greater percentage of successful collisions. Increasing the concentration of reactants in solution increases the rate of reaction, as there are a greater number of particles available to react. This increases the frequency of collision between particles. So this is again like we said, you're on the little small desert island with 10 people versus 100 people. All right, now, increased temperature. Why does this work? So it increases your frequency of collisions, and it increases, sorry, your percentage of successful collisions. And it does this by increasing the temperature, increases the kinetic energy, which means they move faster and with more energy. And that increases the frequency of particle collisions and a greater proportion of collisions which have the energy required to react. That's why it works. All right, now how about this? Why does surface area work? Annabelle, why?
So the frequency of collisions and the percentage of successful.
Yeah, it's going to increase your frequency of collisions, and that's going to affect your successful collisions. And that is because the increasing the surface area of a solid reactant increases the number of particles that are exposed.
Like an elevator, like
The elevator. You're in the elevator with the little skinny guy. You're in the elevator with a giant human. Yeah. Yeah. Who's more likely to bump into you? Right? Or who are you more likely to bump into? Right? And that those particles are exposed and available to react. As a consequence, this increases the frequency of particle collisions and increases your rate. So increasing pressure, this applies only to what? Gas, right? Because gas has no definite volume, right? So this is going to increase your frequency of collisions. Okay, and how? Because increasing the pressure of a reaction involving gases forces gas particles closer together. And this will increase the frequency of particle collisions and therefore increase the rate of reaction. Basically, when you put a gas under pressure, you are increasing its concentration. You're making that gas more and more concentrated, right? It's just like with solutions, more concentrated solutions are more likely to react. And using a catalyst. Okay, we still have to talk about catalysts a bit. But here's what a catalyst does. So if you look, if you are graphing out the reaction rate for a particular reaction, it's going to look like the top line there where it says without a catalyst. And what do we call that amount of energy that a reaction needs to begin? Activation energy. So look at where it says with a catalyst. What do you suppose that means a catalyst does?
Closed.
It lowers activation energy. That's what a catalyst does. A catalyst is a chemical that will lower the amount of energy required for a reaction to proceed.
So is a water a catalyst?
No, not usually. We don't usually think of it that way. I'll give you some examples in a minute. But a catalyst provides an alternative route for the reaction with a lower activation energy. And this means that particle collisions need less energy in order for a reaction to occur, increasing the rate of reaction. So reaction pathways and activation energy. Okay, here we go. Here's our activation energy that we talked about. It's the minimum amount of kinetic energy that particles must have for a chemical reaction to occur. The minimum amount. If they have more, that's fine, but it's got to have that minimum amount. So if you look here, here's an old word. There's a word we know. What's that say over there on the y-axis? Enthalpy. What's enthalpy?
Enthalpy is a change in energy.
Yeah, we measure enthalpy by change, right? But it's the amount of energy in a system, right? There's your enthalpy, the amount of energy in a system. And we can't measure the amount of energy. We can only measure the change in energy. All right. So it shows you where it says reactants over here. All right. And it says there's your activation energy, which is abbreviated as E sub A. You see it up there where it says E sub A, activation energy? Right. Okay. So you need to reach at least this line, the tippy top of that hill, in order for it to start your reaction and go from reactants to products. And in this case, you can see that maybe the reactants start way lower down here with lower energy, and it's going to take even longer. It needs more energy. So you see the one on the right, it's going to require more energy than the one on the left, because you see how much farther it has to go before it hits that peak and rolls over that hill. I saw a video the other day. I probably should have saved it, but it was a guy driving a pickup truck, and I think somebody got this video with a drone. You know, when you go down the highway or the interstate, sometimes there's like a grass median in between. And sometimes on some highways or interstates or whatever, there's no wall. It's just a big grass median, right? And it's usually kind of like this. It's kind of concave. It slopes in. Why do you suppose it would do that? What's going to happen when it rains on the interstate? Yeah. So usually when you see one of those medians, it slopes down, right? So the water can go there instead of standing on the road, right? It's a lower point. All right. Well, this was a video of a guy in a pickup truck in the ice and the snow. The roads had been treated. The roads look great. But somehow he must have slipped on a spot he didn't see or whatever. And he ended up in that little ditch in the median. And he was driving, he was reversing his truck up one side and then trying to get enough energy to drive up and out the other side, but he kept slipping on the ice. He was, oh my gosh, he'd torn the whole thing up. It was just muddy snow, but he had to back up and get himself high enough up the hill on the other side to use that energy to come down and like gun it to get up, right? It's very much like activation energy. He needed enough energy to get up out of that ditch. And he probably went back and forth 20 times in the video I saw. And he'd been doing it before they started filming because there was just mud everywhere. Can you imagine being stuck like, he was just going back and forth, almost like a pendulum, trying to get enough energy to get out of the ditch. You don't ever want to be there. It doesn't sound fun. So this is an example of a reaction where we have C6H12O6 plus 6H2O. And over here, it's going to produce 6CO2 plus 6H2O. What is O2?
Oxygen.
Oxygen. Very good. What is H2O? Water. What is CO2?
Carbon dioxide.
Carbon dioxide. Okay, there are three things in here you recognize. What do you suppose this one is?
What?
C6H12O6. Here's a hint.
Glucose.
Glucose. What's glucose? Do you know what it is? It's a sugar, right? I will tell you what this reaction is, but I want to see if you can figure it out. If you combine sugar and oxygen and you end up with carbon dioxide and water, do you know what that reaction is? It's happening right now, like millions and billions of times in this room. It's happening so fast. I'll give you a hint, it's exothermic.
Breathing.
Breathing's part of it. That's a very good hint. You bring oxygen into your body for a purpose.
Releasing carbon dioxide.
You breathe out carbon dioxide, very good. That's the oxygen going in. You also breathe out water. You breathe on a cold window, you see the fog, right? So you know you breathe out water. So what do you suppose this reaction is?
Breathing.
This is aerobic respiration. That's what that is. So that is the process that gives energy to your body. That's how we produce ATP. That's what makes our body run. So you need sugar to function because sugar is what's necessary for your for you to metabolize, for you to live, right? That's our body's fuel is glucose, which is like it's the same sugar you find in your blood. They make glucose tablets that you can take, but we can convert other sugars into glucose, fructose. We can convert all sorts of other sugars into glucose. And then we use the glucose in aerobic respiration. Well, if you look here, it says you need this much energy, activation energy for it to move forward. And then you need this much activation energy for it to go backwards. So the forward path is oxidation of glucose. And what's the reverse path? What's it say?
The reverse is.
Right here. What's the reverse path?
Breathing in.
Photosynthesis. Did you know that aerobic respiration is chemically opposite, the absolute reverse of photosynthesis? What do the trees breathe out?
Oxygen.
Oxygen. And what do they contain in their leaves? Sugar. They produce oxygen and sugar from carbon dioxide, which is what they breathe in, and water. What is it?
Like something like arteric or something.
What describe?
Like humans breathe in oxygen, sugar, starches, and oil, whereas plants and trees,
Yes, the opposite.
yeah.
Yep,
do
it's the opposite. What were you gonna say?
Trees breathe in the carbon dioxide.
Yeah.
And then oxygen, and they only spit the oxygen.
Yep. So it's basically the opposite. Trees do the opposite process. Plant life does the opposite process of animals. Plants and animals have opposite, and it's important because if we all did the same process, if trees use the same process to produce their energy, can you imagine that we would just run out? We would run out of oxygen if all organisms use this same process. But trees do the opposite of us. Plants do the opposite of us. So it's a nice little cycle that repeats. Do you know most of Earth's oxygen does not come from plants? Do you know where it comes from? Most of the oxygen that is like being produced in the atmosphere isn't coming from plants. It's coming from phytoplankton in the oceans. They produce even more than green plants that are terrestrial plants. All right, so catalysts increase reaction rate. A catalyst is a substance that does what?
That lowers the rate of reaction.
Lowers the reaction energy, increases the reaction rate, but does not change during the reaction. The catalyst doesn't change. So without a catalyst, it's going to require more energy. And with a catalyst, it's going to lower that activation energy to get to the products. Catalysts lower the activation energy barrier. This is what they do. So without it and with it, you can see. And
Without it, it'll take longer.
Enzyme would take more energy. Enzymes are a type of catalyst found in nature. So we have catalysts that we use in lab all the time. But more than that, there are catalysts in nature doing their work in your body, all around you, constantly. And without them, things would be much harder. So an enzyme is a large protein molecule which catalyzes metabolic processes. Metabolic is basically how your body functions, how it manages its energy, produces energy, and uses energy. That's metabolism. Like sometimes like people will say that really skinny people have like a fast metabolism. Like they burn through their energy quickly. So they don't get fat because they don't store extra. Right? They burn through it real quickly. Kids tend to have a higher metabolism than adults. The older you get, the slower your metabolism gets. And there are times when your
Yeah, right,
metabolism,
yes.
right? And there are times when your metabolism will naturally slow to a degree. For example, in pregnancy, you need to maintain as much energy in your body as possible rather than burn it, because you need it to build another human, but you also need to build energy reserve in case you run out of resources. Like, our bodies don't know we aren't living in caves somewhere. So, you know, our bodies are like, oh no, I might not have food tomorrow, so I better hang on to some fat. And so your body will metabolize more slowly and during certain processes, and pregnancy is a good example. Do you know that babies, newborn babies, have a different kind of fat than the rest of us? They have something called brown fat, and it's a special fat reserve that is for a newborn baby, just in case that baby's food supply disappears, or they go a period of time without the food supply. Another fascinating, and it does involve metabolism and enzymes, is do you know that certain marsupials, like kangaroos, for example, can be pregnant with 2 joeys at the same time, each gestating at a different stage? Not like you girls that were there at the same time and started at the same time and ended at the same time and came out at the same time. Kangaroos can have a baby that's, you know, so much developed and one that's so much developed at the same time. They can they don't like consciously management, because it's not like a kangaroo is
So one
thinking about it,
is
you know?
outgrown than the other one.
Yeah, one can be born way late, and they can actually stop the development and like freeze it until the resources become, like if they're running out of water or food, their bodies will stop that gestation and just, it'll be like, you know, frozen for a while until it's time to start gestating again. It's pretty wild. Humans can't do that. It's pretty wild.
It's like twice as short as you.
Yeah, sometimes that happens. It can be. It can also be like how they developed. Like, I went to school with a set of twins that were, yeah, boy-girl twins. And the girl, for whatever reason, like she got more nutrients and stuff, like when they were developing in their mom, than the boy did. So she was born like big and strong, but the boy was born like really, really weak. And he was like, you know, he was in the NICU and stuff, and it took him a while to kind of catch up. It was not even. The development wasn't even. And she teased him all through high school. She called him Golden Boy because he was like special, because his family treated him all special because he was so fragile when he was little. So. And then it didn't help that he actually got run over by a fire truck when he was little, which like made the Golden Boy thing even worse. So, and he was in the hospital in a body cast for like 2 months because he got run over by a fire truck. Yeah, a real one. Yep. So these are examples of some enzymes, all right? And enzymes are proteins. Proteins are organic molecules composed of amino acids. We're going to talk about this later in this quarter when we get into our organic chemistry or hydrocarbon biological chemistry. So they are big, long molecules, but they're folded up in a very particular way. Have anybody ever used an old map, like the kind that your grandparents and parents used to have to use before there was GPS on your phone? You ever used a map like that? When you open up one of those maps, it's like darn near impossible to fold it back up the way it came. Like, it's just really hard. You have to fold it a very specific way. Yeah, it has to go real specific. And that's kind of how proteins are. So here's an example of proteins and how they work. And enzymes have what's called an activation site. And it's basically like a lock and a key. It's a specific shape. They're looking for something called a substrate, all right? And that substrate has to be the exact shape to fit that enzyme. So it's like you have, it's like, do you remember in Harry Potter when they were looking for the right key? Does anybody know that scene?
What movie?
The first one. Do you remember before they,
Yes, the flying key.
the flying keys, and only one key fit the lock they needed? Kind of like that. Or imagine yourself, you're in a room full of filing cabinets, and you have 100 filing cabinets, and you have 100 keys. And each filing cabinet has only one key that will work on it. And you have to you have to try every key till you find the ones that work.
It's 1 in 100.
Yeah, that's exactly how substrates and enzymes work. It has to be the right substrate with the right enzyme. And then when they combine, they make the product. And the product leaves and then the enzyme remains because catalysts don't change. So some examples are pepsin, which is in your stomach, sucrase. And this is interesting too. The names of enzymes often describe what they do. Sucrase breaks down sucrose, which is a sugar. Amylase which is in your pancreas, breaks down amylose. Urease, which is in your liver, that breaks down urea actually. Trypsin in your small intestine, lipase in your pancreas. Lipase breaks down lipids. So it'll often tell you what it does based on its name. So reaction rates, and now that we've talked about them, they can be measured. Obviously, they can be measured because we said it's a measurement to begin with. It's a measurement of a change over time, right? And there are different ways to measure them. We may see a change in volume. We may see a change in mass. We may see a change in pH, a change in electrical conductivity, or a change in color. And today in lab, you're going to be watching a change in color occur. And it's going to occur at different, but this time it's going to occur at different times. And you're going to watch it change over time. It'll be kind of fun. I promise. All right, so concentration must be measured often. So what is a reaction rate? How could we measure the reaction rate? You can measure the concentration of A as it decreases or B as it increases. Remember back to our purple and green particles a few minutes ago in that graph? You could measure it. I asked you both questions, didn't I? How many green are there at this time? How many purple are at this time? And if you know how many you start with, like remember we started with 50 purple and 0 green, and we ended with 50 green and 0 purple, right? If you know where you're starting, then along your timeline, you can take measurements of either your decrease in your reactants or your increase in your products, right? And you can do that by testing the concentration. Yeah, of course. So reaction rates can be represented graphically. We've seen that a bunch now, a whole bunch. Here's another example. Amount of product formed over time. There's your original reaction. You can make it faster by adding a catalyst. You can make it much faster or much faster. So you could have added a catalyst. We could have increased the temperature. We could have increased the concentration. There's lots of things we could have done here to affect this reaction rate. But do you see that this is the same reaction every time, but it's getting faster and faster and faster based on changes we're applying to that system. All right, rate laws. Yeah.
I just want to say, my mom has really bad type 2 diabetes. I mean, you know, if she eats, one time she ate part of a fried onion and she threw up everything she ate that day.
Ew, that's not good. That can also be a gallbladder thing because you need the bile that's produced in your liver and stored in your gallbladder to break down fats, emulsify fats, and you can get sick that way too. So we also have something called rate determining steps. So rate determining steps is the slowest step in a reaction. All the different parts of a reaction come at different speeds, and there's one step that's slowest, and that is going to determine your overall rate because you can't go faster than your slowest part, right? If you have to drive, if you have to drive 25 miles an hour in your neighborhood, but then when you get out of your neighborhood, there's no speed limit, the thing that's going to determine how fast you're getting where you're going is the slowest part. Like you can't go faster than the slowest part, right? So it shows you here that sand, if this were an hourglass and the sand were falling through, that rate determining step is that first step. You see, because it's got to go through that slowest part there before it moves anywhere else.
Lucy, do you have this one?
No,
2 brothers.
I'm the only girl.
And then we have intermediates, species that form but then are consumed. So that'll happen in your lab today. You'll actually create, there'll be a product that's created and then consumed again, and then it keeps moving along. Homework. So you can actually look at this right now and know what your homework's going to be and start thinking about it. Research enzymes in the human body. You're going to write, it's going to be your homework. And you're going to write a little bit about something you learned about any type of enzyme in your body and how it works. There are lots of different enzymes in your body. And that's what you're going to do. Do you know of any already? Can you think of any already that you know about? None right now? Stu Christ would mention that. Yep. So you're going to do a little research. Yeah, there's lots of them. You're going to do a little bit of research and see what you come up with. Cool? All right. So you're good. Let's get ready for lab. Let me tell everybody to come in here. All right, y'all want to come on in?
The thing.
Yeah, you want this one?
Thank you.
Yes. Let me see. CJ. Come on. In here. See, James and Okay. I'll tell you your teams in just a minute, or whether I get in first. I'll tell you, just be patient.
No.
Oops, I'm sorry. Oh, PJ, here, take take this, Caitlin, and take yours. That one's PJ's, this one's yours. Where's your, hand that to your brother, if you don't mind.
Yep.
Yep, thank you. All right. Hmm. All right.